Hi, my name is Nicholas Wiley, and this is Homework 6, Part 1 for Material and Energy Balances. And today we're going to be looking at vapor-liquid equilibrium. So to start, I thought we'd read the problem statement. So for the first part, we must derive the expressions that can be solved for the due temperature, due pressure, bubble temperature, and bubble pressure for an ideal mixture of n components that follow Raoult's law. Now, what we're going to do with this is we're going to use, I'm just going to read part 2, we're going to use our equations for a mixture of benzene and toluene to calculate these specific numbers, these specific values, the due temperature, pressure, and bubble temperature pressure. And then we are going to create plots of the binary vapor liquid equilibrium phase diagram at a constant temperature and then at a constant pressure. So before anything, I just want to talk about what's really sets this problem apart from what we've done all year. So the big thing about this is that we have a mixture of n number of components. Now, what does this mean? We will be using the Antoine equation as we have in the past. However, what the Antoine equation does is it gives us this pure saturation vapor pressure for pure substances, but we're going to be looking at mixtures. So what we're going to need to do with our 30% benzene and 70% toluene is we're going to have to use sums, which you're going to see to figure out what each of those values is when we convert to the Antoine equation for benzene and toluene respectively, using those mole fractions in the liquid and vapor forms. And yeah, let's just hop right into it. So the first thing that we want to know about this problem is that in the system there is equal amounts of liquid and sorry, that's not what I meant. The total mole fraction of liquid is going to add up to 1 for each of these. So knowing that's a pretty useful thing to know. I think that we might as well just hop right into this. So when we look at the right side of this equation, the total pressure, so the vapor mole fraction times the pressure is actually going to equal our partial pressures for each gas. So what we can do with that is we can set up a summation, making the left-hand side equal to the right-hand side. So I say that we just hop right into it. So we're going to get our pressure is going to equal the summation of the partial pressures, which is a very common equation. But since this is a mixture, we need to add this summation to the right side as well. That's the whole reason we're doing this. So when we're looking at this, we have our right-hand side taken away. So now what we need to do is, insert this as it is. And the reason that we can do that is because, like I've said, we know this value. We know the mole fraction of each in the liquid form, but we also know, because we're at a set temperature, the due pressure is going to be the point at which the first bubble, the first I wouldn't say drop of vaporization, but you know what I mean, the first second that any form of vaporization happens, that is going to be our bubble pressure. So, okay, I think that makes sense. Pressure, yes. And since we know the temperature, both of these are known, and we can pretty easily calculate this bubble pressure. Now, when going through this, here, just moving on. So now when we want to look at, so this is our bubble pressure, P bub. So now what we have when we look at the bubble temperature is now we are holding pressure constant and we are trying to solve for this temperature. Now, looking at this, we see a big commonality. We have this term right here, but this also appears in our Antoine equation right here. So what can we do? Rather than having that, which is dependent upon constant temperature, now we're changing our temperature, so we're going to substitute that in, substitute our Antoine equation rearranged in for that. So what we can do is we can do the same thing. And then what we're eventually going to do is we're going to use this in Python to give us the answer using a root solver for our bubble temperature. But that's for the next video. For now, what we'll do is we'll just rearrange this. So we again have our liquid mole fraction multiplied by, once we substitute that in, we are going to get, I believe, 10 raised to the A minus B over C plus T. So now what we're going to have to solve for is this T right here. Up here we're solving for that bubble pressure, which we can figure out very easily because these are knowns, and if they're not knowns, then we can figure them out pretty easily. Here we know this, but we're going to have to do a lot of rearranging to figure out what our bubble temperature is. Now moving along, another big fact about all of this is that we know that the sum of the mole fraction in the vapor phase is going to be, actually, that's wrong. We know what I said earlier, we know that the moles, the sum of the different mole fractions for the liquid phase is going to equal 1. So what we can do is we can use our equation from before, which was simply, I believe that it was P bub is going to equal the summation of our liquid mole fraction times our pure saturation vapor constant. So since we know this, what we can do is it's a pretty simple rearrangement of the problem. What we're going to do is, and since this is bubble, or this is dew pressure, again, we're going to be using this because we know the temperature. So this is perfect. This is perfect for us because this can be figured out. But this right here is equal to 1. So what we're going to do rather is we're going to rearrange our Raoult's equation. So then once we do that, what we're going to get is divided by P. So now what we can do is, since this is like this, what we're going to do, since this is equal to 1, we can just make this equal to the right-hand side. So we'll have our vapor mole fraction multiplied by our total pressure divided by our pressure of saturation, Pi sat. Now, since I think the best thing that we can do for this problem is what we can do is we can do this. I'm just going to write it out and then explain why I'm doing so. What we're going to do is we're going to draw that P out. And what that's going to do is just make our calculations a lot easier later. So this is going to be our dew pressure calculation. Because what we're going to do is it'll be a simple rearrangement. Actually, we can arrange this even more. I don't know why I did that. So now what we can do is we can make, what we're going to do is we're going to do 1 divided by this so that we can get straight up just our dew pressure. Is going to equal the summation. Wow, that was an ugly summation. So it's pretty much using what we know and putting the puzzle pieces together to create these equations. It's not deriving, it's just rearranging what we know into equations that can be used for us. Well, and we're just going to raise this to the -1 rather than drawing that big fraction, big ugly fraction. So now that we have this, we can pretty much follow what we did in the last step. So with this, the reason that we can do this is because we know this, we know the pure saturation vapor pressure with this because we know the temperature, still on the topic of the dew pressure. And we also know this, and what we're solving for is this pressure right here. So what we can do is just like in the last step, so since we no longer know this, since we are looking for temperature, we know the pressure, what we can do is reorganize this again. Just like we did before, we just replace this with the temperature, and then it's going to take a little bit of figuring out some root solving, and we're going to be able to determine the dew temperature. So is simply replace that with our 10 to the A minus B over C plus T. And then again, yes, so we know this pressure right here. We know the total pressure. So what we're going to do, this is pretty much going to be a constant. We know this value right here. If we don't know it, then we can figure it out. And right here we have our Antoine equation. And that is going to, since we have that summation, that's the reason it's going to work. It's going to take both of those pure compounds, that 30% benzene, that 70% toluene, that percentage is going to become very important when it comes to the coating. But either way, because we have that, we're going to figure out each of the components, and we're going to be able to determine the bubble temperature based off of comparing it to pressure and all these other factors. So in the next video, what we're going to do is we are going to code for these, and then we are going to plot the binary vapor-liquid equilibrium phase diagram at constant temperature and pressures. Thank you for watching, and I'll see you next time.